Okay, welcome back after lunch. And now we have Hae Young Kee, her second talk series, and she's going to continue with her discussion of Kitaev Materials and Kitaev and sub-Kitaev Materials.
Yes.
So we're looking forward to it, and it's 1 hour and 20 minutes with half an hour discussion.
Yes, thank you, Pierce. So this is just for Sweer, who has missed my talk yesterday, to define what's the Kitaev and sub-Kitaev. I define a Kitaev as where the Kitaev interaction is the largest in the full Hamiltonian, while the sub-Kitaev, meaning it's sub-leading term. And candidate material that I'm going to discuss today is going to be mainly a ruthenium trichloride. And then we will talk about a little bit about the chromium triiodide, which in fact is a higher spin state. I appreciate that Pierce saying that we will continue the discussion because I don't really have much conclusions to present. It'll be mainly open questions. A lot of things are still unclear in this communities as well as the field. I think it's evolving somewhere, but I think the effort from the community has been great so far, and we are looking forward more of the collaborations and talking each other, try to find out what's going on in this interesting material. Okay, so theory side that I presented yesterday was much more clean. It's a microscopic theory, ideal systems. And we see a kind of, okay, where you got a Kitaev and gamma interaction and there's a Heisenberg. But when you're dealing with the material, we are confined with the reality. And I know Pierce once called me that you're dealing with the beast, but I think I'm trying to find the beauty of the beast. So let's see what happens with this ruthenium trichloride first. And I'll see why I pointed out this might be the nature of unknown X phase that are responsible due to this particular two interactions. Okay, so here's my outline. I'm going to talk about the experiment. Since I'm a theorist, I definitely don't have full understanding. So those who are in the audience and those who are in the Zoom, if you can correct me if I make any mistake, please do so. This is an hour and 20-minute discussion and a talk. So hopefully that you can join me along the way. You don't have to divide into the speaking and discussion. I prefer to be interrupted during the whole session, whole hour and 20 minutes. And then I'll talk about the Kitaev gamma models, about the theory part. And then what is the effect of magnetic field? And talking about Kitaev pressure field, which is different from this exactly solvable model that Kitaev proposed, because we do have a Zeeman term, which are not that small. And then I'll talk about Kitaev gamma pressure field. And then if I have time, then I'd like to talk about the higher spin model, which is a spin 3/2. That's probably a chromium triiodide or nickel diiodide, and some of those triangularis might be also related to this particular model. And then I'll summarize, but summary is mainly, as I said, will be only open discussions. Okay, so transition metal trihalide, as I told you yesterday, from the microscopic point of view, we like to have a D5, we like to have a honeycomb, multi-insulator, and narrowband where interaction is very, very huge, and spin-orbit coupling. Then if you look at this table provided by one of the review article, I'm sorry that I missed the citation for this table, that existing materials for the D5, there's only iron compound, X is anions of halide, and then there's a rutheniums, and osmium doesn't exist, but even osmium exists, you have to also worry about a bit of dimerizations in actual system. So ruthenium does exist, so we thought that, okay, this is the best. So that's where it comes. Here is a ruthenium trichloride, and that might be one of the candidates for the Kitaev material. So that's where we start. And then I digging up the literature and trying to see where this material, since when it existed. In fact, that I traced back to 1892. It's very old material, apparently. This paper in the second column, second row here, it's a journal of less common metals. Apparently, it's not that common, but I was told from experimentalists, ruthenium trichloride is actually, you can make it in the lab quite easily. So back then probably was less common metals. In any case, this is a very nice paper. And then there you can find a lot of history about that old days and how you make it. And there are two forms that appears. One is alpha and there is a beta. Alpha is the layer structure with the 2D, quasi 2D. Beta is like a 1D chain-like. In any case, back in the old days, people know that it was insulator. Here is the 1 over the temperature, and the y-axis is electrical conductivity. And you can see that this is a low temperature here, so it's going to be, and this is a logarithmic scale. It's a pretty good insulator. It's a damn insulator. As you see the title here, 1970s, it was known to be a semiconductor. And 1980s, 1996, I think this was probably, at least from my understanding, is the first paper where Polini here start to discuss that this might be a multi-insulator. Due to the strong correlations, it might be a multi-insulator. Pay attention about this space group here. It's told something about the stacking of the layer, which might play the role in an actual system. It was known to have this particular space group, but apparently that's may not be the case. So magnetic ordering below appears in the below the I'll call it TC, but it's a TNL. Some kind of zigzag order patterns appears, and as I told you yesterday, that all of this candidate material has a magnetic order at low temperature. We are trying to find the reminiscence of the spin liquid at finite temperature if this phase are nearby. Okay, so here the susceptibility is very anisotropic. It's AB versus the C-axis, and you can see that the C-axis is hot axis, and that has something to do with the gamma interactions. If the material has the very small trigonal distortion, here's some specific hit. And if you look at the specific hit, look at the down in here, it's a derivative delta Cp. You see a nice peak at 7 Kelvin. There's another one at 10 Kelvin. There's another one at 13 Kelvin. All of these are known to have a stacking disorder. It's like a van der Waals material with some different stacking along the C-axis. Okay, here is the elastic neutron scattering and shows the nice intensity difference between the two temperature. If you look at the elastic peak, that appears around the 7 Kelvin, and that shows the magnetic order, and that has a pattern of the zigzag by looking at a momentum places, and that has been confirmed by many others. So it's quite well established. Now, what about the T above the T now, and what about inelastic and dynamics? And as we discussed yesterday, that maybe a small interaction sets the magnetic order, but there are other large interactions such as Kitaev might be the one that governs the high temperature phase, as well as some kind of dynamics like a high energy state. So here is a nice work done by people. Well, there are lots of work done by the Stephen Naglers, as well as the Ramans done by the Ken Butts. You can see the Raman spectra has some kind of continuum, which we had discussion. A lot of Radu was talking about the continuum at a cobalt materials. And there we also see some kind of continuum here in the Raman. Inelastic neutron scattering shows the nice continuum at a I think this is about 5 or 7.8 or MeV, and that is persisting both below and above the nil temperature. So that has indications of some strong frustrations, and was claimed that this is a proximity to the Kitaev spin liquid. And I believe Stephen Nagler was made a great contribution towards this discussion. Okay. And after that, people start thinking about, is there a possibility that we can induce the spin liquid by the field? And that, I believe this is the first paper, but if I may be wrong, but I just think that here is a magnetic field along a certain direction. And here's some kind of magnetic ordering patterns. Before it polarizes, there's some kind of spin liquid. And here is the plaquet order parameter, which is the product of the 6 spins going around the plaquet of the honeycomb here. And that is the one that commute with the Kitaev interaction. And that's what we like to compute because of that, because there is a reference point of the Kitaev where this number has to be 1, expectation of this operator has to be 1. Here you can see that there's some changes occurring in the middle, and that's probably why we start, thinking like this might be some kind of spin liquid. And there has been lots of experiment followed after, and I don't think I have time to go through all of them. So I'll just jump into this thermal transport. Recall that the Kitaev has predicted that if we have this Majorana excitations around the edges, we'll have the half integer quantize the thermal Hall conductivity, where C is supposed to be half. And the rest of parameter here is a universal constant. And that's what they see. Here is the Matsuda's very first experiment as a function of temperature. And this is a much zoom out view. And here is a zoom in view. If you look at the very low temperature here, there's a bit of quantizations with the eyes of lover, you have to see it. And there is a magnetic field. This place occurs in a range of the magnetic field and range of the temperature. So it appears at a temperature range around 7 to 9 Tesla, and then only along this temperature range of 4 or 6 Kelvin. And lower the temperature, this kind of disappears. So that was the big claim, and people start jumping into it. And then they start to rotate the field. In fact, that this experiment was suggested by me. I actually told him that you can rotate the magnetic field direction as you cross the b-axis. Remember, the b-axis is the special because the b-axis is the field which is the parallel to the one of the bond. And remember, I called the C2b, which is a pseudo mirror symmetry, and that is preserved. And because of that because of that mirror symmetry, it's a pseudo mirror. It's not a conventional mirror symmetry. Because of that symmetry, we are not going to see any kappa xy. It has to be 0 by the symmetry constraint. And that means that if I rotate this field, which go through the b-axis, kappa xy has to be then 0 here. And then that has to change the sign from a +½ or -½ because your Chern number of Majorana has to change. So this is a zoom in view of that too here. And you can also explain this by just looking at the Kitaev's original time reversal symmetry breaking term here, Hx, Hy, Hz, basically rotating the magnetic field from here to the other direction. You can change Hx, Hy, Hz. But I must say that this actually goes beyond the pure Kitaev. You can just look at the generic spin model and just to show the symmetry, and one can show that the sign change, like these pictures here, where the kappa xy has to go along the b-axis, which is this direction, is the generic to the Hamiltonian. All right. Okay. Now, so after that, we were very excited, but at the same time, we were a bit concerned that this experiment has to be reproduced and so on. So there have been people who have been working on it and had a hard time to reproduce the data. And there has been a lot of discussions about whether there are sample dependence and so on and so forth. So here's a paper from the Yamashita et al. And you can see that the first one here is what that I wanted to emphasize. It's susceptibility. And it's here's around the magnetic ordering temperature. And above the magnetic ordering temperature, here's supposed to be some kind of paramagnet or something here, or something that is governed by Kitaev, whatever. But you see that the susceptibility itself has a sample dependence. Here's the kappa XX. This is the longitudinal. It's a longitudinal thermal transport, and then this one is another one just with the different samples. And here's a sample called A. So you can look at the A samples, sample called A at a different temperature, 4.6 Kelvin, 4.1, 3.3, and you see this little plateaus. While if you go to the B and C samples, which are the these samples, then the half quantization is not there. So apparently what the claim was that the sample A, which is this one here, is the one which has a large kappa XX, is the one that see the half quantizations. In other words, the lattice has to be very clean to have the large thermal transport is the one that shows the kappa XY to be half quantized. But when I see this, I thought that, well, I think that having the susceptibility itself, having a sample dependence at a finite temperature here is telling us something more significant than just so here is the other two sets of the data. So left side here is from the Panong's group, and the other right side here is from the Hide Takagi's group. Both of these are showing a thermal Hall transport, kappa XY, as a function of the magnetic field. And then different colors, different temperatures in both cases. And if you just look at the two of this, we might say, well, this data looks very similar or like each other. But the claims are quite opposite here. This paper comes with a title saying the robustness of the quantization. So here's a half quantized values, and the group of people claim that there is a robust half integer kappa XY that develops in a certain range of the magnetic field, which is slightly different from the 7 to 9, but it is a little higher, like 8 or 11 Tesla. But here, what they claim that, well, we don't see a half quantized values. It's actually just goes through. It just arises, kappa XY arises as a function of the field and also arises as a function of the temperature. On the other hand, Panong's group here has quantum oscillations in a kappa XX. So longitudinal ones start to oscillate as if there is a Fermi surface, just like a metal. When you have a metals, we will have some kind of quantum oscillations coming from the metallic Fermi surface. But as I told you, this is the DEM insulator. It's a very, very good insulator, and we don't have any carriers to generate such oscillations. But this is a thermal, so it's an entropy. We don't have, this one does not necessarily require the charge to generate such an oscillation. Whatever the particle that carries entropy is enough to generate such oscillation. So the claim was that probably this is a quantum spin liquid with a finite spin-on Fermi surface. Okay, that's really exciting. It's going more and more exotic, but then this paper came out just about a few days ago from Takagi's group, showing that this oscillation is not a quantum oscillation, but it looks like it's a sequence of the magnetic transition. Okay, so here is again the kappa subtracted some kind of background. I'm sorry that the left side is not shown, but this is like a kappa XY going back in here. This is like that one here, and you subtract the background to see these oscillations itself, and that's what they are showing here. And there are two different samples, apparently. I told you there is a strong sample dependence, and there's a name for a CVT. I don't know what it means, but there are two different ways of growing it, CVT versus the Brisman here. So these two are two different samples. I believe the CVT is the Panong's group, and Brisman here is the Takagi's group. Anyway, one or the other way around. But anyway, they have two different samples with a two different space group, according to them. And you can see that this one is exactly different samples. And you see this minima of the oscillations matches each other. So independent of samples, apparently there are some magnetic transition that it's matching. And here is this is just magnetic field, again, parallel to the A-axis. This is a DMDH. So you are taking a derivative of magnetization as with respect to the field. And you can see this nice peaks here, which is representing some kind of magnetic transitions. So here is their samples, and they also see this nice peaks here, and that's just the different magnetic transitions. Okay, so right-hand side here further is actually a temperature, and the field. And you can see that the phase transitions from one zigzag to another ones and another ones. These are all different magnetic transitions when the field is along the a-axis, which is the perpendicular to one of the honeycomb bond. So that's the current situation. Okay, so I don't have I don't have my personal opinion on this, but I think I am gonna remind you about the C-axis stacking, why that becomes important in this discussion. So this is a quasi two-dimensional samples. Unlike the iridate, we don't have alkali metal in the middle of the two. It's just the van der Waals. Given the van der Waals potential, we know it's very weak. The difference between the different stacking. So here is one of the stacking seen from a side view called the P3112. This is the one that was initially thought that we had old samples. People thought that this is the stacking. Modern ones, we believe that we have C2M, which is a bit of monoclinic distortion. And then this one is the one that I told you in the back of 1996. They thought that this was their stacking along the C-axis. If you look at from an ab initio, which don't take the numbers literally, but it gives us some intuition that, well, at least confirm our intuition that the energy difference between different stacking is only 1 MeV. And we found from this ab initio calculation, the old stacking has the lowest energy. So here is about 0 here. And these two, which was proposed by other days and times and with different groups, in fact, has about 1.4 MeV difference. And these two are actually degenerate even. They don't even have a different energy. So in other words, stacking can easily change by even small magnetic field. So that's something that one should worry about. And the reason that why am I worrying about this? And some people might say, well, since it's a van der Waals potential, the C-axis coupling, let's call J-pop, is going to be small anyway. So why do you worry about it? But that is small, that's okay. And we don't need a J-pop to have a finite magnetic order because we don't have SU2 Heisenberg model. We have just discrete model. So in principle, given that we have finite gamma, which makes the easy axis, the hard axis along the C-axis, generate the spin gap and so on, this will give us provide us a finite nil temperature. But what happens, as you see it here, these 4 different columns are different relaxation. So we want to relax the structure, and then depending on the condition that we relax, we end up with a slightly different lattice constant and a slight different bond angle between the ruthenium and then chlorine and the ruthenium. And if you recall my first talk yesterday, that the most contribution from the Kitaev interaction is the hopping process from the d orbital to a p orbital to a d orbital, because the p orbital is very close by. And that interaction or that hopping is strongly depends on the distance between the ruthenium and an angle. And therefore, depending on the structures, even though they are tiny difference, you can see that this hopping T2, which contains the largest contribution from the p orbital, is going to change drastically. And due to that change, exchange interaction can also change. So the one that is robust is actually an anti-ferromagnetic gamma, which seems to be rather there. But Kitaev itself can go from positive Kitaev to a negative Kitaev and can grow. And Heisenberg is still always a negative here. And then there are still small gamma prime, which comes negative, and that's due to the trigonal distortions. Yeah.
So I think there are like few experiments on that.
Yep. Yeah, so yeah, if you have a monolayer, depending on how you grow them. So for example, if you do it with the encapsulate with the graphene, which people do, then you end up with a bit of the strain from the both side. In that case, there are other problems. So there you have to also worry about now what is going to be, that will give you different numbers. And if you did grow on one of the substrate, then you break inversion symmetry. Bottom and top is different. You generate the Zaluzhinsky Moria interaction. So then your microscopics will also change under the condition of your growth. So I would worry about some of the details before I jump into the fact that, well, we found the G2 spin liquid. Maybe there is an even U1 spin liquid with a finite Fermi surface. Just want to remind you that I didn't talk about the rest, but the process of JK gamma is rather complex. And the reason that one can change the Kitaev sign is because there are two terms that contribute. This is the DPD most important that I talk about. And that term dominate, you end up with a ferromagnetic Kitaev. But T1, T3 is a combination of two, is coming from a direct hopping, and that generates anti-ferro Kitaev. So depending on the competition between direct and indirect, one can actually change the Kitaev signs. All right, so and T1, T3 actually comes with opposite signs, by the way. So they usually add up from a chemistry of TPD, pi bonding versus the sigma bonding. Okay, so in the phase diagram, even without worrying about gamma prime, which is small enough, one can move from here. I told you that the most of material sitting in here with the ferro Kitaev, and then this is all thing is anti-ferro positive gamma interactions. One can move from here, move there, but all of these are within the zigzag correlation. I told you that this yellowish meaning that it doesn't develop the magnetic long-range magnetic order within that 24 site, but it has a zigzag correlations. If you introduce the small gamma prime negative ones, it'll develop the zigzag order. But that means that in fact that the magnetic order, the moment direction also tell us about the microscopics, the strengths of them, and that will also change as you move from one to the other. So in other words, what I'm saying is that samples will be sensitive to the stacking. It's not because J-pop is changing, but you can change in-plane exchange interactions. As you change them, zigzag magnetic order can also, it is still zigzag, but the moment direction, say within the AC plane, can rotate into another directions. So all of this will tell us if your samples, where they are located in the phase space. It was shown by, I think this is also Stephen Nagler's group. It's very nice work. The zigzag here, this is again magnetic field along the A-axis. They do see the pattern changes indeed. Here's the zigzag 1 and then zigzag 2. And the difference between the zigzag and zigzag 2, or they call 3F versus the 6F, it's a number of the layers that involve the zigzag coming back. It only are 3 layers versus 6 layers. So apparently there is a change from the pattern through the in-plane magnetic field. Okay, so and I thought that, well, let me think about this. Well, maybe, there might be some people have done how the van der Waals potential can change under the Zeeman field. And I wasn't able to find it, but I was able to find this chemistry paper. Well, it's a PRL, by the way, but I think this person is UBC, the Department of Chemistry. In any case, what it means is that the van der Waals molecule, it's 2 atoms. And we know from quantum mechanics that the van der Waals potential, molecule is formed, and you can show that there is a minima here, and that is the best location, optimize the energy with the next atom sitting in. But what this is showing is that with the small Zeeman field, if the atom has a partially filled with a finite angular momentum, that potential can shift all the way up, and molecules break down, become 2 separate atoms due to magnetic field, and they combine again. There's a lifetime associated with this, and it's really interesting paper. And what we have is indeed partially filled. We have finite angular momentum, L equal to 1, and we have finite spins. And so our case might be even more complex than this, but I'm just saying that one has to be careful about the chemistry and what's going on before we jump into disordered quantum spin liquid under the small in-plane magnetic field. So that's the experimental side. I just brought up some of the things that one may have to consider. Okay, so if you have any question, I'll take it. Otherwise, I'll move to theory part now. Is that okay? Okay, so minimal model. Here is a list up to 2020. All right, and I thanks to
You may short to ask a question.
Sasha here, and they give us this list. And if I've missed anyone down here, and not my fault, you should talk to Sasha. Sasha, he's the one who has made this list. So it's complicated at this stage, but I just make the block here because you can kind of go through it and then notice that what are the dominant interaction. And dominant interaction is still the Kitaev and gamma interaction. Most of them has the ferro-Kitaev interactions, and gamma is anti-ferromagnetic. And this anti-ferromagnetic you can see everywhere here. So at least that doesn't change. Here, the Kim et al. Is what I showed you earlier, and you can see one of them has this positive Kitaev, and that's what I told you, that with the old P3112 space group, it just have a different stacking, you end up with the different Kitaev interactions. But apparently it's a ferromagnetic Kitaev, and that's where we are going to start. So I'm going to say that minimum model is Kitaev gamma model. And then we are going to add the small interactions and see what happens. And that's already a difficult problem because I'm going to rotate the first. That was the old phase diagram because I'm going to use of interest in this line here, because that up and down is depending on the Heisenberg. So we'll be interested in this horizontal line, and I'm going to call that my x-axis from now. So my x-axis is the one that changes from ferro-Kitaev and then going through the gamma, anti-ferro gamma here, and then anti-ferro Kitaev. So going along that lines, what is happening in this model is already complicated enough. Okay, so here's the idea. Well, we say, okay, dominant interaction is the ferro-Kitaev plus the gamma, and then there are other small interactions, gamma prime and J3 or Heisenberg, all that coming in and set up the magnetic ordering in the material. And then what happened is that, okay, I'm going to apply the magnetic field and destroy this magnetic ordering, and then we are going to reveal the phase which is set by Kitaev plus the gamma. Of course, if I don't have gamma, I'm going to get the Kitaev spin liquid. So that one is clear. But once I have a gamma, then the situation can be very different. So then the question is, what is the phase of Kitaev and gamma model? And that is, again, another controversial that comes in. So if you have a pure Kitaev model, yes, we know that this is the Kitaev spin liquid. Thanks to Kitaev, it's an excellent problem. Pure gamma limit already controversial. So here is the various different work done by numerical method, ED, DMLG, and then there's variational Monte Carlo, and there's another DMLG, and so on. But all of this except one in here says that the pure gamma model is disordered, and we don't find any magnetic ordering. This part here is a variational Monte Carlo, so one begin with the variational wave function, so there could be bias. All of other things have their own limitations due to the finite size effect and so on. So one has to take this with a grain of salt because these are all has their own limitations. But if you look at the classical spin, it's a very nice work by the Natasha and Ionis that if you look at classical gamma model, it has the macroscopic degeneracy. So here's a gamma model has been taken by these people here. And one can show, just like a Kitaev classical Kitaev was solved by others, and it's called Cartesian spin liquid. It's a classical spin liquid. You can introduce so-called eta variable. It's called eta 1, eta 2, they call eta 3. And one can show that you can satisfy this bond energy along this honeycombs and everywhere, but left with this eta variable, which will be eta 1, eta 2, eta 3, which are defined on a plaquette. Then what happened is that all of this state where I can change the sign of eta from +1 and -1. So eta can change the +1 and -1. And that maps to, they are all degenerate. So the sign of eta does not change the energy of the classical gamma model. So this is like a mapping into triangular antiferro Ising model, which is one of the known, like almost the first known frustrated magnet. And that classical ground state degeneracy grows at 2 to the n/2. And one can show that this is indeed classical spin liquid. If you have a sign of antiferro gamma, they further show that quantum fluctuation does not destroy does not select the magnetic state. If it has a ferro gamma, it seems like there is some incommensurate magnetic order that can build up. Okay, so now, so I want to show you a couple of examples of the numerical work. Despite that they have their own limitation, they give us still some ideas what's going on. So here is the K and gamma. As I said that we are going to use x-axis. Here is the ferro-Kitaev, anti-ferro-gamma to anti-ferro-Kitaev. There is an exactly solvable point, which is sitting in the middle here with the angle of the 0.75. We are using some cosine and sine to make the from one limit to the other with just one parameter phi, and 3 pi. It's 3 pi over quarter is here is is a 1/4 multiplied 2. Okay, so anyway, it's a 0.75 is where this is SU2 point. So when we know that there is a magnetic order here, but other than that, there is no magnetic order. In fact, the magnetization is completely dead. And these are static structure factors. This one is the ferro-Kitaev point, and here's anti-ferro-gamma point. These are magnetically ordered state, and we don't really see much of ordered state. Okay, so we do find that the ferro and gamma has a wide range of the disordered phase, and this was also done by DMLG calculation. So here's another DMLG done in 2018. Here is a ferro-Kitaev here, and then anti-ferro-gamma, and there's an anti-ferro-Kitaev. There is a transition between the ferro-Kitaev and anti-ferro-gamma. So there is a sharp transition here. So here's a Kitaev spin liquid, which are kind of a little bit cut off. Sorry for that. It's a tiny area here, and there's a wide range of this disordered state where magnetic ordering is 0 here. And these are dynamical structure factors showing that here's a ferro-Kitaev, and I believe this one here is the anti-ferro-gamma, and seems like a pretty flat structures here. It's hard to see what is in fact much going on. Okay, so now let's add a magnetic field and see what happens. This is already starting with the disordered state. So adding a magnetic field on the already a disordered state, we'll see what happens, but I'm going to add some small interaction to generate the zigzag order and see what happens under the magnetic field. Before I do that, this is another nice work by the Simons that has done just the Kitaev, press the magnetic field. Okay, why we are doing so? Kitaev already had a Kitaev press the magnetic field, but remember the magnetic field that Kitaev has introduced has the 3 spin terms, which is Hx, Hy, Hz with Sx, Sy, Sz, and you can show that if the magnetic field is small compared to the Wison gap. In other words, magnetic field is not going to destroy my G2 spin liquid. In that case, you can expand it. And once you expand it, that's the term that you will generate. So precisely Zeeman term with the strength smaller than the Wison gap, one can get the Kitaev terms. But as you go beyond that, then of course, it's not clear where we are going to end up. So Zeeman field is not the same as the time reversal symmetry breaking that Kitaev has added. So here is the numerical calculation done by these people. Ferro-Kitaev and anti-ferro-Kitaev is very different. Of course, anti-ferro, just like anti-ferro Heisenberg and ferro Heisenberg are extremely different. One is the classical state, the other is not. It's a nil state, it's not the same as just the classical anti-ferro. Anti-ferro-Kitaev is much more rich compared to the ferro-Kitaev. Ferro-Kitaev, in fact, that if you have 1% roughly, numerically, of the Kitaev strength, you can kill the Kitaev spin liquid. It's rather interesting because the Wison gap calculated by numerical calculation is about 6% of the Kitaev interaction. But if you have a 1 or 2% of a field, we actually just destroy it. And then we just got an all polarized state around it. So ferro-Kitaev is apparently very unstable and just every spin is just polarized. Huh?
How do you know that the instability is so immediate?
Oh, this is a numerical calculation. Even the Wison gap is a numerical calculation. All of these are numerical calculation within a sum size. So we don't know exact numbers. All I'm saying is that the Zeeman field strength smaller than the Wison gap strength. You can kill it in the ferro-Kitaev. On the other hand, anti-ferro is the other way around. So even here, if you look at the one of the directions, so here's 111 is along the C axis. 112 bar is the A axis. this is a field that people have applied in the experiment. And then here is 1, 1 0 is the b-axis, where the pseudo, the meter is not broken. So we don't expect to see any kappa xy here. And it doesn't matter in the ferro-Kitaev, it's done. Here, the Kitaev spin liquid is very stable up to quite a range of the magnetic field. In addition to that, they have something they call the Yuan spin liquid. So there's a spin-on Fermi surface actually show up. So if the actual material is sitting in the anti-ferro-Kitaev, yeah, I mean, we got everything, right? So I can get some zigzag here and then get some G2 spin liquid and get a U1 spin liquid before you polarize. But apparently we are sitting in here. So then there is a big, and if you have this situation, there are lots of other experiments that doesn't fit it. So we are nearby here, then what is happening? Okay, so that's here, I said ruthenium chloride 3, maybe it's near the ferro-Kitaev. So how do we understand this? So you're back to again this phase diagram here. And I'm going to introduce small gamma prime. You can introduce J3 as well to stabilize the zigzag around here. And then move along this direction. So here is a ferro-Kitaev, and I'm moving along this direction by introducing anti-ferro gamma, increasing the anti-ferro gamma interactions. And this is 24 site ED. Okay, so it is limited by the size of the system, and I cannot capture like a big size unit cells and so on. So here's what we have found. So here's a Plaquet operator. Again, expectation value of this is plotted here. So, and this direction is the this arrow here. I'm moving from ferro-Kitaev to a gamma, but not up to the pure gammas. It's just the small gamma that we have introduced. I flipped the other way around because I want to compare this with other studies. And one study has done it this way, and the other study has a meter of this. So I flipped mine to compare with other people have done it. So here's the zigzag order. And this direction of the field is out of the honeycomb plane. So it's a 1, 1 on axis. And I'm rotating my field within the AC plane here, not a B, because B is not going to do anything to me. So I'm going to change the angle of the theta from 0 to 90. And that'll be, if I go in this direction, that's exactly what experimentalist has done. So this area is going to be experiment. And out of the plane direction is the this phase diagram. So here's the magnetic field, and here is the gamma is increasing. And we found, okay, there's a zigzag here, and there's a wide range of some disorder state that we have found within the 24 site. And that is gone as soon as we tilt the field. So this one is a theta equal 5 degree. And if you do the C-axis, there are lots of things appears here. And if we do like just like experiment along the A-axis, this Kitaev spin liquid is confined in a tiny, tiny space, just like what I said. And then all of this is just a polarized state. By the way, this polarized state is not a conventional polarized. It's not yet polarized because of those interactions. So even this polarized state has still partially polarized and so on. So
what are the axes? Sorry, everything is flipped. So the axis, x-axis is gamma prime here?
no, gamma. This is the gamma. X-axis is gamma. So I'm introducing. Yes, anti-ferromagnetic gamma is increasing. Yeah, here's a ferromagnetic type. So that point corresponds to here.
Yes.
And then I'm moving towards that direction.
And what is the vertical axis?
Vertical axis is the strength of the magnetic field. And these two are different angle of the magnetic field. Just the contrast angle. So here's a 5 degree away from the C-axis. And here's a 90 degree, which is A-axis. And this is experimental situation. So nearby the zigzag, we have Kitaev spin liquid, but that's like a tiny area. Everything is dominated by product state of the some partially polarized state. So, so we thought that, well, wow, this is exciting because I mean, the idea is that the gamma is the hot axis. So I know that if I apply the field along the C-axis, which is hot axis due to the gamma, we might end up with something, and that's precisely we found, but we are not sure if this is a quantum spin liquid, and we thought that it might be even connected to the Kitaev spin liquid.
How did you determine the top boundary?
Huh?
Yeah, that boundary there.
That boundary here?
Between the polarized state and the QQS.
Yeah, this boundary is coming from 24 site ED, so it's not very clear it's a real boundary or not. I'm going to show you the other one who's done it much better job than us. Well, at least motivated by our studies. so I just want to emphasize intermediate spin liquid is not found when is found in the when gamma is finite, while it's almost gone once you have just the pure Kitaev. So here's another work done by after us, motivated by us. It's infinity tensor product state study. It's done by these people here, and it was also later on done by IDMLG people. So here's that's why I rotate my meter dip, because I want to compare with this study where we had it the other way and they put it this way. And I think this is more natural. So I'm going to use the gamma over K here. So here's a pure Kitaev, and here is a finite gamma. And they introduced small gamma prime, just like what we did. It's basically exactly what we did. So here's a zigzag here. Here is the flux WP, the values, they become 1 here. And this is a magnetization, so here's a zigzag order. And they found that the, let me remove this quantum spin liquid a little bit. Oh, I cannot do that here. Okay, anyway. So they found that the, here's a so-called pneumatic, they called it pneumatic paramagnetic. So in other words, they don't find any magnetic ordering appearing in this state other than the one that has been applied. Okay, so this one is again field along the either z-axis or 5-degree rotated. It doesn't matter. It's the same phase diagram. If you apply the field in the in plane, I write it here. They don't find anything just like what we found in the 24-side ED. But what they found is the Kitaev spin liquid is confined within a very narrow range. And then they found here is called pneumatic paramagnet. It's disordered. Difference between Kitaev and here is that the C3 symmetry is broken. It's like a pneumatic in a, like I remember yesterday, we had a question about the scale lattice with the XX bond and YY bond. Yeah, and I got an email from Guinea saying that, well, I would think that that would be pneumatic. And I think that's what I think is right. So, and even, triangular lattice in a Kitaev, you can also get a pneumatic. So it's really speaking about the compass model. The compass model has this tendency to try to become one bond to be stronger compared to other. Unlike the scale lattice, where one bond is stronger than the other, then its SX is stronger. So it's like Eisen chain. Here is not, because you have a 3 bond. 2 of the bond XXYI differ from the Z bond. So it's like more like a coupled chain. And that's what we are finding here. And that is now the real question is whether this is a quantum spin liquid, which is a topology behind or beyond broken C3 is not known. So this could be pneumatic star, MP star, where the star, meaning where you might still have fractionalization, which I believe so, may not be a Majorana's, because I know in the 1D Kitaev chain, you can have a half fractionalizations, for example. But in these studies, that is not discussed, or at least it's, they are discussed, but there's no conclusion based on this. Okay, so here's some classical studies done by Leon Chan, who is here, so he can correct me if I'm getting anything wrong here. And so here's some classical spins. Of course, we don't expect to have all that, but you can see it's such a nice, a lot of, large magnetic, this is a number is referring to the size of unicell. And you can see like a 50 unicell size versus 98 that appears. All of this become like a pretty messy, but it's speaking that it's really frustrated. Here's a machine learning studies. This one is not only going from a ferro Kitaev, which is sitting near here. And then here's a gamma, anti-ferro gamma. And they say this classical spin liquid survive, this is a magnetic field along the z-axis. So they still survive gamma spin liquid. Ferro spin liquid Kitaev is here, and there's a cooperative paramagnet. So here again, it's different from, or this is just a polarized state here. And then here's anti-ferro Kitaev, which survives also quite high, and so on. Okay. And this is experiment done along the z-axis. Y-axis is not a scale, looks like a log scale or something. It's a 20, 40, they've done it all the way 140 Tesla. This is the magnetic field angle. So they rotate from the z-axis towards the a-axis. you can see that by the angle of 5, this unknown, they call quantum spin liquid, disappears and become a zigzag to a paramagnet. So it's again different from other experiment. So here I'm back to my first slide that I start with that we want to discuss, that the starting with some x-axis here, which is some interaction, that this is the Kitaev spin liquid, and we introduce some interactions which generate the zigzag order. And we say, okay, if I have my material which are sitting nearby, then this physics here, finite temperature, may be governed by the Kitaev spin liquid, right? Because this is a 2D G2 spin liquid, and Subio has a wonderful, discussion for us before this talk. So that means that we might see some reminiscence of this, but I have other axes here, which is the magnetic field. And I have shown you that this Kitaev spin liquid is confined in a tiny area. And then we have seen something else that pops up, whether that's pneumatic paramagnet, or it could be just a polarized state or forced and ferromagnet, some people call it. Depending on what this is, and also depending on this boundary here, as a function of temperature, what happens, where we are sitting at finite temperature may not be that clear that this is governing, or this X phase is what that governs. Or it's not even clear whether this boundary will survive all the way to finite temperature. That will depend on the nature of this disordered X. And we don't find disordered X when field is along the A-axis, unlike the experimentalists that found something interesting going on when field is along the A-axis. So we are seeing only near the C-axis. So that's I would still leave it as open question. That seems like we didn't make a goal. I started with the warm up, and I've done the all build up, and I didn't get the goal. Just like Liverpool, which has just lost the Champions League to Real Madrid, but we have next year, so we'll see what happens next year. All right. Now I'm just gonna switch the gear and talking about the higher spin S Kitaev. So we're talking about the Kitaev and going through the microscopic theory. We talk about, okay, it's exactly, yeah.
Give us like the bottom line from the numerical work.
Yeah.
For ruthenium chloride.
Mm-hmm.
What is the final? What is the current understanding?
Okay, so I cannot talk about the current understanding of other people. I can tell you current understanding of mine.
That's what I was just.
Okay, good. Okay, so I'll tell you what I think, and there are people, there, so they are allowed to disagree, and of course, and I think the A plane, when you put the field in the A axis, I implied it, but I didn't speak, and Severe is forced me to speak about it. If I put the field along the in plane, I think there is a stacking appears. In other words, stacking fault will start to show up, and due to the fact that van der Waals potential is so weak by the 10 Tesla, I would think that there are other stackings which might change my in-plane exchange interactions. So before we clean up and have someone like just really a monolayer, even you've encapsulated by the graphene where you have a strong strain, but again, it may be still mapping into some kind of Kitaev plus other interactions. Without doing it, I don't think there is a way to tell that is Z2 spin liquid or even U1 spin liquid or anything like that. So my personal opinion is still you have to wait.
Same space diagram where it's a functional field, you have the ZZ order or something.
Yeah. Mm-hmm.
And then there's a spin liquid, and then or some intermediate region. I guess the bottom line is, are there 2 phases or 3 phases?
Yeah. So let's go here.
So ZZ I count as 1.
Yeah. So ZZ here and ZZ2 is a 2 different stacking of the ZZ.
Okay.
And then when people are talking about the spin liquid is outside here,
Yeah.
and I'm saying that these are all might be related to the other stackings.
I see.
So until we know what is really happening with the stacking due to the magnetic field, I would rather sit it in a conserved area and say, we still have to check it out.
But there's no numerical study where, say, at 8 to 10 Tesla, you get a spin equation.
Numerical study, there's nothing here. It's a completely polarized.
Or the ferromagnetic.
Ferromagnetic Kitaev with anti-ferro gamma. You can add J3, you can add any other. There are many people. I'm sorry that I didn't add a lot of other people's.
So 110 is
no, this is a different. Yes, it is. It is supposedly 112 bar based on the common notation. I think this is a slightly different notation that they are using. This is the field that people have used, which is called A-axis, which is the direction of the zigzag shape.
And everyone's putting the field in that direction.
Yes.
It's easiest,
Yes,
or-
that's not everyone. If you go back to the earlier data by first data here, you can see that the field was rotated towards the C-axis. You have a slight tilting angle here. So there is a C-axis component as well as the A-axis. And you can
Okay.
still have it here. And after that, people put a in-plane. And the reason putting an in-plane in a lab is because you can access this, you can kill the zigzag order by the field that is accessible in the lab, because it's a 7 Tesla is enough to do so. If you put a field start to rotate along the C-axis, gamma is antiferro, which give you hard axis. That means that to kill the magnetic order, you already need to have about 40 Tesla to get in there, apparently, according to this experiment. And I think that's what makes the situation much difficult. So here is the C-axis experiment. Zigzag order survives all the way to 40 Tesla. And this experiment was done in the place where you can get the over 100 Tesla magnetic field.
But as a
There.
function of theta is not, but the conclusion is still the same. So they're only getting theta equals 0 here.
Yeah, so that's a C-axis.
C-axis. So no one's ever done an experiment up there.
This is only experiment that they've done it. Only one experiment with the C-axis. There is other people, is a Modic et al. I believe this was even earlier than this particular paper. They've gone through, you can see this, the dimers, triangles and things like that. So they've done quite a large magnetic field. Due to the gamma, even in a classical ones.
Claim there's a QSL. Right?
Yes, they claim that there is a QSL. This can be done in the theory. So theory can produce this, but not in the A-axis.
Okay, so theory does give you a QSL?
Yes, theory does give a disordered state. I wouldn't claim a QSL because we don't know. It's a numerical calculation that shows that there's no magnetic order.
Okay, and the theory of ferromagnetic.
Yeah, theory for ferromagnetic plus the gamma interaction. Without the gamma, you don't get that.
Sure, of course.
Yes.
And theory says there's some sharp phase position, well, at 120 Tesla from QSL to PM.
Yes, yes, that's what theory says.
How
If
do
you have a
points-
field
how
along
do
the
their
ship.
points at 120 Tesla? Oh, that's calculation. This is a mixture of that.
Oh yeah, apparently there is a calculation and there is an
Some
experiment.
points are all calc. I see. Okay. Interesting.
Yeah, and that's another calculation that I didn't cite. So it's there are other papers which confirms what I have said in terms of theory.
This is quite amazing. This is positive.
Mhm.
Do these calculations take into account the shape, the interplay of the spin orbit coupling and the higher JZ multiplets? Or do they just factor those out of the discussion? Because presumably those are going to be mixing in as you start to apply fields in different directions.
Well, okay. So first of all, J effective half doublet. If you look at the time reversal, they act just like a spin half. Now, yeah, and then the 3/2 is separated by lambda. In this material is about 100 MeV, and then we are applying a field of 100 Tesla, which is about 10 MeV. So I don't expect them to be very, very strongly renormalize them.
It'll be Van Vleck effects, right?
Which might be, yes, because it's not, but that will be small. That will be, I would expect to be small. But in any case, Van Vleck is the next order to begin with. If you have partially, if I have a partially filled, I have a Zeeman term, I have, the linear term to begin with. So, and then Van Vleck is like a what? I mean, I have closed shells and you go to the H to the square orders, you'll still get a Van Vleck effect. So I think I would expect to see all of this with the Zeeman is enough to worry about. So this experiment is very close to what the theory has predicted. Well, I don't see anything here in the zigzag to polarize.
None of the theories predicted quantum spin liquid. You're faced with the situation that either theories haven't included the correct details about the real system, or you're faced, or you discount the experiments.
No, we don't discount the experiment. I mean, that's why we've been searching so hard. It's not just myself. There are lots of community. There are people in the German, like Rose Valentis, and lots of people have been doing. So the ingredient that, so I think there are two things. For example, so let's begin from here. So we are in the, let's say that I have a largest interaction, which is a ferro-Kitaev, and I apply the Zeeman field. I'm going to polarize everything. And of course, so we don't even have a zigzag to begin with. So we need to add something to begin the zigzag order. And then ask ourselves, what are we going to get if I apply the field? And there is a huge anisotropy between in plane and out of plane because of the gamma interaction, which I strongly believe it's there because it's a very anisotropic system. So, we, so we are taking some, we are trying to working hard to try to see try to realize the experimental situation. And someone like me, who was, one of the first people who have proposed that this material is supposed to be a candidate. So I like to see them, of course. I have a strong desire to see it, but it's just, we don't see it. On the other hand, we may be completely wrong, and we might be sitting in here. If you're starting from antiferro-Kitaev, let's go back in here, the phase diagram. And who knows, I'm sitting in here. Antiferro-Kitaev with a small Heisenberg is enough to give me a zigzag. That zigzag magnetic moment is a different direction by the magnetic moment direction. We also tell you a little bit about it. So we know that it cannot be here.
Still got many possibilities.
Yes. So we if I have a here with the small Heisenberg and then antiferro-Kitaev, no antiferro gamma, I could be somewhere here, but then I'm wrong with the magnetic moment direction. So if you want to fit it into the different sets of experiment, it's hard to avoid that we are somewhere here and then zigzag is introduced by the J3 or gamma prime. I mean, doesn't matter. One of them is enough to give a zigzag order. Then once we have that situation, we cannot get any spin liquid or disordered phase once I apply the field along the A-axis. We just go directly to a polarized state, partially polarized state. Then whatever they are seeing in the experiment, one has to be careful because there is a stacking fault that may be generated due to the Zeeman field, given that van der Waals potential is very weak.
Stacking faults mean the layers.
Yeah, layers are stack, stacking fault, they move. Yeah,
Really?
they can slightly change, and that changes the chlorine position. If you change the chlorine position, it's with a slightly angle, and as I show in the van der Waals molecule, they can dissociate. Molecule become an atom under the Zeeman field. The one that I show was a helium oxide. You just need a 2 Tesla to make the molecule just to become atoms. And then they bind it again because there is a different way they can bind. So there's a lifetime associated with this molecular binding and then atoms molecular binding. And I wonder if something like that may happen. And that's what this earlier, the most recent experiment that I'm showing you here, that under the magnetic field, you see a lot of different magnetic transition. Okay, that doesn't mean that this is not a spin liquid. Of course, you can still have SL star or GG star. I mean, of course, that is not, I'm not excluding that possibility. But before I jump into that possibility, I think one has to really clean up the stacking problem in the actual system. So that's my point of view at this point. Yeah.
Is there some way
in a sense of how strong the interlinear coupling magnetically?
Yeah, so if you're thinking about just energy-wise, it's only 1 MeV. So interlayer coupling will be, I don't know, it's going to be even smaller. But interlayer coupling is not the whole point. It's interlayer coupling is small. So initially I thought that, well, I don't have to worry about it. But then, I recall that it's not just of interlayer. You slightly shift your p orbital. As soon as you change that, your exchange path is going to strongly renormalize your exchange parameter.
So it's inherent to the van der Waals
Yes.
nature
Yes.
of these materials, which is very fragile.
Yes, exactly. So given that this is van der Waals, you can shift them, and then chlorine position gonna adjust it. And as soon as your chlorine is adjusted, your exchange parameter is gonna be different. And the what in-plane exchange is going to be different. And that because the chlorine is out of the plane, it's not, they are just out of plane and the bottom of the plane. So the cubic octahedra, which cubic crystal field, you have a ruthenium here. There are 3 triangles of the chlorine is out of plane. 3 triangles of chlorine is below the plane. So they are here, and they can make the different squeezing, and that can change your exchange parameters. The one that is most sensitive is actually a Kitaev interaction. Gamma is not changing much, neither Heisenberg, neither gamma prime. So it's, I think it's a sensitive. One has to be careful about this scenario. And I mean, this is just appeared Hide Takagi's group. And my personal opinion is aligns with this concern. Yes, Leon.
Just as a comment on the Karen's and Simon's. So I think there's a suggestion that even you have a ferromagnetic effect plus other interactions like J gamma, right? But there's a self-draw transformation that can be made to transform this model into one closer to the anti-ferromagnetic. There's a possibility in this U1 spin.
That's an interesting point.
Self-draw transformation also proposed by Hae and his collaborators.
Yeah. Yes. Which I believe requires pretty large gamma prime, but
yeah.
Yes.
It requires, significant
other terms. Yes. Yeah. And I think there is a nice work by Rosa Valentis group where similar things has been done, where they see the intermediate state. But again, if they put it in plane, she agreed that they don't find any intermediate phase once the field is in the A-axis. So that's the theory community has been having a hard time to reproduce the quantum spin liquid when the field is in the plane. Yeah, if anyone disagree, you can write on the Zoom chat. Please do so. How am I doing in time? Do I have time for a?
You have 18 minutes.
Okay, great. So that's
You're right.
okay. So let me just 8 minutes. Thank you, Pierce. You want to give me an extra 10 minutes? Okay, so let's just have 8 minutes is probably enough to go through quickly about this possibilities. Yeah, so as soon as your spin is more than half, let's say 1, 3/2, and so on, this is no longer exactly solvable. And then classical spin model was done. I mean, it's has shown by Bhaskaran et al. And they also have shown that for any arbitrary spin, this WP here, you can define different from the conventional spin-off. Defining this, in fact, will have well-defined, and this will have a short range correlations. But beyond that, we don't know much about it. We don't know spin 1 is spin 1, spin 3/2, is that quantum spin liquid or ground state, or because we don't know the ground state, we don't know the excitations about the ground state. So we don't know if this is Majorana fermion or fermions or complex fermion or bosons. Is there any difference between the half and half integer and the integer spin Kitaev? And all of these are not known. something is known in the 1D chain of the Kitaev, and so I don't have time for that, but at least the 2D case, it's not known. Okay, so numerical studies was also done earlier days. This is about 2018. They have seen the entropies here, with having a half quantized values before it fully polarizes. Fully getting, so here's the temperature. And then these people here actually propose that the spin 1 Kitaev might be a gapless spin liquid. And that's a numerical study, by the way. I have some of the work done, but I think today I just want to tell you briefly how you can get the spin 1 Kitaev or spin 3/2 or 1 and so on.
So that study was just pure Kitaev.
Yeah, this is just a pure Kitaev. Yeah.
For this case, the sign of K doesn't matter.
Yeah, for this case, sign of K doesn't matter. As soon as you introduce other interactions, sign of Kitaev matter.
Right.
Yeah, because one is become very unstable, the other is still can occupy quite a phase space. But at the pure Kitaev limit, positive, negative doesn't matter. Yes. So this is just the pure Kitaev model. We like to understand how you get the spin 1 Kitaev material. So here's a higher spin Kitaev interaction. So I told you that you need a spin-over coupling. And that spin-over coupling is going to entangle the wave function. And that wave function has a colorful red and blue. And that is needed to get the bond directional spin interaction because orbital is the bridge for your spin interaction. If I want to get a spin 1 or a spin 3/2, I need Hund's coupling to be the larger scale because I have to align it. Once I align it, I'm losing my spin orbit entanglement. So I'm going to get, for example, easy orbital. This is the D8. For example, nickel diiodide will be one of them, but it's just a triangle lattice. It's not a trihalide, it's a dihalide. So, but in any case, you can have a D8 compound with the Hund's coupling very large, and then this is a spin 1. So I don't have any orbital spin entangled. Energy scale is the crystal field. Cubic crystal field is always largest, and then Hund's is the second largest, and spin-over coupling is very small. So that means that this is spin 1 or spin 3/2 is going to be my wave function to begin with. No mixtures of different spin or the orbital. Orbital is frozen here because I just got both up and up. So how we get the higher spin? You can go through the heavy anion. That's why I'm talking about iodine, not the chromium chloride trichloride. I need something that's much heavier, and iodine have spin-over coupling. Atomic value is about 800 MeV. It's even much stronger than iridium, for example. So here's a heavy iodine, which will have p orbital, and that p orbital will be splitted by the spin-over coupling. And then we are going to go through the process of the exchange using these heavy anions. Okay, so we are doing exactly the same thing that I did yesterday, hopping between the two different M sites via heavy anions. And there are 3 kinds of different ones using the cubic symmetry. These are some of the details. And I'm not going to go through the same thing over that I did yesterday. So let's just jump into the conclusion. If I just have indirect, which is the necessary because I need to go through that heavy anion, then I'll have a Kitaev interaction. And that comes with a twice larger than the Heisenberg. And that symmetry is related to the easy orbital. I have a completely filled T2G. And then in this process, I'm just using an easy orbital. So easy orbital has some particular symmetry with the cubic environment. Then we end up with the Kitaev, which has opposite sign of the Heisenberg and twice bigger. And because of that, Heisenberg is going to be antiferro here. Kitaev is going to be antiferro Kitaev. If I go just direct hopping, direct is going to give me a Heisenberg with the positive sign, and gamma is going to come with up to the 4th order is 0. So I can just ignore it exists, but it's a perturbation theory. So high orders will give me, but it's small enough that I'm going to ignore it. So if you do that, we end up with the Hamiltonian. It's again ideal cubic. Okay, I don't have any distortion yet. Ideal cubic with the spin 1. You can go through the heavy anion. We'll get the antiferro Kitaev with the Heisenberg interaction, where Heisenberg will have competition between the indirect and the direct. So that means this can be small. So in this case, one can generate Kitaev material with a spin 1. And this is antiferro. So that means antiferro Kitaev is stronger or robust under the magnetic field. So one can probably get something much more, like a robust under the magnetic field. We've done small size ED here just to show that there's a disorder state, which is over the J over K. So here's a pure Kitaev, two different curve at two different sides of the ED. And then one is a zigzag and the other is just antiferromagnet. Just want to point it out that there was an ab initio calculation, which has a similar idea from an ab initio. So I like to give some of this reference as well. Okay, so again, near the antiferro, we say that in a spin-half case, this was much robust compared to the ferro Kitaev. So is that so for the S=1 Kitaev, antiferro Kitaev? Are we going to get anything interesting out of here? And that was the addressed by the numerics again, because it's not exactly solvable. We have done the ED. You can see that there's a collapse of the the spectrum, which show up, some intermediate field here. So even in a spin 1, we are seeing something interesting going on in an intermediate field. So here will be some kind of Kitaev antiferro spin 1, something interesting happening. And then this is a polarized state. You can see the gap is linearly growing as a function of the field. So that's kind of trivial state. So here's a dynamic structure factor, left to right. One is a spin 1 and the other is spin half. I don't know which is which, but you can see the similarity between them. And then specific it, you can see the similarity between the spin half and the spin 1. If I don't label, it's hard to differentiate. Also, let me label it here. Here's a spin 1 and here's a spin half. So there is not much of difference between the two, other than the fact that there is something here going on, but there seems to have intermediate state, which is stable. I just want to comment that spin 3 half model, also you can have similar stories. So with the T2Z, and that's precisely this chromium triiodide is the one that will falling into this category. And we suggest that this might be a candidate sub-Kitaev material because the Heisenberg interaction is the dominant one. As I told you, the Hamiltonian is like that. If you introduce the trigonal distortion, we have to again deal with a bit of lots of different terms. All of this become rather small, but we have to deal with it. Like a spin-orbit coupling with the frustrations, the distortions will generate the single ion anisotropy, and that is responsible to generate the gap. So this is a chromium triiodide. People talking about single layer. This was a single layer compound. And there is a finite TC with a single layer and talking about, well, you need some gap, spin gap to generate the finite transition temperature. And so this cannot be a SU2 ferromagnetic Heisenberg. So there has to be some anisotropy coming out. And well, I think it's not only the anisotropy comes out, in fact, that more than anisotropy comes out. There is a single ion anisotropy that generates the gap and protect the state and give you the finite TC. And in addition to that, there is a Kitaev interaction that's finite. And the reason I believe so is because of this angle-dependent ferromagnetic resonance that I briefly talked about yesterday. And remember that the field with two different field angles, which are related by the C2A symmetry, is detecting this term that I call JAC, which is K minus gamma. Gamma is very small in this material because it's only introduced by the distortion. So let me just remove it. Kitaev is just coming in without the distortion. So it's this is what that determines the Kitaev interaction. And the angle difference between the two is detected by resonance difference between these two, because this and that are relayed by C2A symmetry of the field angle. So that one, that you see a big separation between the two different angles, is the what is going to tell us the size of Kitaev, and it changes as you change the angle from 0 to the 90 and get back to. Their zeta is defined from the c-axis. Unfortunately, my zeta was defined from the AB plane. So, but you can go from one angle to the other is basically blue and red. It's differentiating between these two angles. And the field was done in the AC plane, precisely what we want. And this in-plane, out-of-plane is measuring the anisotropy of the single ions and other terms. So here's our fitting using the some exact diagonalizations. It doesn't have much size dependence because it's a ferromagnet, in fact. Then you can see the two different resonances are separated by the Kitaev. One can estimate, and then that's about 40% of the Heisenberg. Heisenberg is a ferromagnet because it's a T2G, which is a field. You go through the easy orbital, and that gives you the ferromagnetic interaction. So it's a little bit of details. But in any case, Kitaev is not small, unlike other people have claimed. So here's inelastic neutron data, which is the colorful ones. I don't know if you can see the black here. Black is our fitting using a linear spin-wave theory. It will actually nicely fit, consistent with so this data, this fitting is done with both inelastic neutron as well as the angle, angle dependent ferromagnetic resonance. So I claim that in this system, and then Dirac gap is here in the K point, which Radu also talked about, but not this compound with something cobalt, but some of this might be also interesting to think about. So there is a DM interaction that one has to worry about. So I don't have time to go through any of those, and I don't think it's that important. But the Kitaev interaction is actually quite significant. Okay, so here's my summary. Sorry that I rushed through it a little bit in the back, but yeah, as I said, today I don't have much it's not very clean at this point because when you're dealing with the material, I want to stay as realistic as possible, but at the same time have to balance with a theory that can provide, of course, there are limitations of the theory that is numerically, well, which is known, we still need to develop further. But in any case, this bond-dependent interaction is just required from strong spin-over coupling, either at a M, which is a transition metal, or anion site. Either of those is enough to generate some kind of interesting physics. And using a symmetry of the Hamiltonian, one can single out the size of the Kitaev interaction. That was yesterday talk mainly. And today I leave with a lot of open questions here. Basically, we still cannot answer if the Kitaev materials, despite that the Kitaev interaction is the largest, if you have ferromagnetic Kitaev, is that governed by Kitaev interaction, or is that the interplay between the Kitaev and gamma is going to be the one that kind of dominates the physics at the finite temperature is not known. There are sample dependence from experimental side, and then thermal Hall, I think one need to clean up the sample dependence to look at the further, to claim that it is indeed Kitaev spin liquid with half integer quantized value. So with that, yeah, thank you for your attention. Yes, actually.
Yeah. Can I ask a question? Do you hear me?
Mm-hmm.
Yeah. Excuse me, can I ask a question? Do you hear me?
Exact diagonalization calculation, like Anderson, Maria, and like Jekeli, and I don't think their calculations can take this into account. So I'm wondering, did you sort of bootstrap off of their results for the case of an anion with negligible spin order coupling, or have you had a chance to think about this three-center exact diagonalization calculation for the super exchange?
Yeah, I'm not aware of three-center. So could you elaborate a little more about that?
He did some three-center calculations for
Uh-huh.
the super exchange, for instance.
Uh-huh.
So that was one question. And another question is, when I've looked at simple models for chalcogenides with selenium ions, I was actually surprised by the extent to which the non-negligible atomic spin order coupling of selenium seem to have very negligible effects on the T2G orbital physics. So it really seemed like it was very strongly suppressed compared to what you would expect. What role you would expect it to play if you just naively look at the strength of the atomic spin order coupling. So I was wondering to what extent you have explored these issues of suppression, basically, of the effects of the atomic spin order coupling of the anion sites on the physics of basically the orbitals of the transition ions.
Yeah, so so one has to be a bit careful about when we are talking about atomic spin-off coupling. So having a large atomic spin-off coupling is not sufficient, for example. For example, if you look at the, what's the best example? Let's say vanadium, antimony, what is this? The Kagome metal. That one of them, which has been very exciting at this point. The Kagome metal antimony is heavy, so you might say, well, is that spin-off coupling important? With the vanadium is 3D, so we don't expect to be very large, but antimony is heavy. But given that when the spin-off coupling to be effective, you see that if they are like, if they don't cross each other, even the p orbitals, if they don't have degeneracies, I mean, they are going to be negligible effect, right? So I don't expect to have any impact. And indeed, in the ab initio calculation, you are not going to see a much difference between with without spin-off coupling. So that's expected, and that's what we see. But if you have a situations where, so this is the, well, there is a metallic system, by the way. Here is a local physics. I'm beginning with some kind of insulator. So here I'm saying that these heavy anions are going to kind of provide the exchange paths where their where that goes. Their spin-off coupling is going to be split here. Is going to be there. There I can just have atomic spin-off coupling is enough. Of course, they are far from the chemical potential because these are p orbitals. And of course, they hybridize. It's not something I cannot ignore. I mean, they hybridize. That's why we can go through the super exchange process. Yeah. So I think it depends on the energy levels of the system. You have some cases you have a strong effect. Some cases you don't. Yeah, okay. Thank you.
Can I still ask a question?